We are slowly building up our integration toolbox, and that's what we're doing in Chapter 3. We developed first a strategy of integration at the very beginning of the course. That's our change of variables, U substitution. And then we got to integration by parts, trigonometric integrals, the families of integrals with sines and cosines and secants and tangents. And then we have the trigonometric substitutions that force sines, cosines, and secants and tangents. And now we're going to go ahead and see how to handle the general class of rational functions. Okay, we know how to handle, things like 1 over x, 1 over x squared, and of course 1 over x squared plus a squared, which is a arctan type integral. We also know by extension 1 over x squared minus a squared and 1 over a squared minus x squared. But what about combinations thereof? What about other kinds of rational functions? And this is going to be the method of partial fractions. Okay. In this part one, we're not going to do any calculus at all. In fact, we're going to show the algebra behind the partial fraction decomposition. And then in the subsequent parts, we will talk about how to do those integrals after we know about the method and the recipe. Now, before we go on to the problems, I want to stress that, again, partial fractions is not inherently a calculus thing. And as you see here, I'm opened to the OpenStax pre-calculus text. It is in section 9.4, and where they explain the partial fraction decomposition. Now, as you can see, okay, the idea is to break apart, say, a scary looking fraction like this into a sum of two parts, because in the end we want to integrate. If we're asked to integrate this thing on the left here, that doesn't look obvious how we can manipulate it, but if we can somehow break it apart on the right, well, this is a sum of two functions whose integrals I know. And so we'll go through the method and the recipe. Okay, so this part is no calculus. We are inherently just going to look at the algebra involved. So if you ever need to refresh yourself on the algebra, just go to your favorite algebra reference here, partial fractions, because that's really all you need, because in the end, the integrals will be very easy. Now let's go ahead and look at the problems. So we want to go ahead and first show the recipe here. And the recipe is to first factor your denominator as best you can, okay? And then you're going to write a sum of fractions so that each factor gets its own thing, its own term on the right-hand side. You'll see what I mean here. So let's say that I want to take this fraction here, 1 over x minus 1 times x plus 2, and want to break this apart into two simpler fractions, okay? Well, I can easily do that, right? So the idea here is that if we take a look here, I have two linear factors here. These are distinct. Okay, these are distinct linear factors. Okay, let's write that here. Distinct linear factors. So when I have distinct linear factors, basically I go ahead on the right here. Each of those denominators is in its own fraction. And the goal is to break this up so I can find two numbers, let's call them capital A and capital B, so that when I add these two fractions together, I get the thing on the left. Now, how does that make sense, okay? Well, let's think about it. Well, let's say I found these numbers A and B, okay? A times x, A over x minus 1 plus B over x plus 2. And I'm asked to add these fractions. Well, adding fractions requires a common denominator, so let's go ahead and do that, okay? So I'll multiply the first fraction by x plus 2 over x plus 2. Okay. And then the second fraction, I'll multiply by x minus 1 over x minus 1. And now you can see that both these fractions have the same denominator, so I can go ahead and smash them together. Okay, just add across the top. So I have a times x plus 2 plus b times x minus 1 over that common denominator, x minus 1 times x plus 2. And the idea here, okay, we want to find a and b so this holds. okay? And we want to make sure that the top, okay, because originally we want it to be equal to 1, the top here, so I'll box these in red. We want to find A and B so that once I combine all the terms together on the top, I get a 1, okay? This is basically doing the adding and subtracting of fractions in reverse, okay? So this is how we handle distinct linear factors, okay? Now, if we look at part B here, okay, well, we see that I have one linear factor here, 2x plus 3, but this other one, 2x minus 1, has a power of 2. Okay, so I'll go ahead and highlight this one in this bright green here. Okay, and in the same color, okay, I'll write down that we have a repeated linear factor. Okay, so the factor in green is an example of a repeated linear factor. Now, when I have a repeated linear factor, okay, I need to still write a fraction with that thing as its denominator. So I'm still going to have something of the form a over 2x minus 1. But when I add the fractions, I still need to somehow account for that second factor, that second copy of 2x minus 1. So what we're going to do is we're going to put down another copy of 2x minus 1, but instead it's going to be a square on the bottom now. And the top is going to be a constant b at worst, okay? Now we can think about this again once we write out the last term here, okay? The last factor is distinct, 2x plus 3. It gets its own denominator, and that's a c right there. So I need to find three numbers, excuse me, a, b, and c, so that that relationship holds up there. Now again, why do we need this extra 2x minus 1, okay, when we have 2? Well, if I added those fractions together, right, okay, 2x minus 1 and 2x minus 1 squared, okay, those are multiples of each other. And remember, for adding and subtracting fractions, we need a common denominator. And relate this back to, like, say, if we have 4 and 16. Well, 16 is a multiple of 4 already. So at the best, I could just go ahead and choose 16 as my common denominator here. So that's going to be the same reasoning here. I want to choose perhaps a common denominator here that includes already 2x minus 1 squared. Okay? So this is how we set up for when we have repeated linear factors. Okay, we'll see that again here, but I don't have this thing factored already in the denominator. Well, not to worry, factoring is an easy job, right? Notice that I can factor the denominator. I have an x cubed, okay, that's common. And then what's left over? Well, we have x minus 1. And so now take a look. I have x minus 1, which appears once as a factor. Then I have 1 over x cubed. That's really x minus 0 cubed, okay? So what's going to happen is that I'm going to have 3 copies with the x. So I need to count up all the way to x cubed here. So x squared, x cubed. Each of those gets their own constant. And then for the x minus 1, I have another constant, and that's its own fraction. And that's how we do the decomposition for when we have repeated linear factors. Now, you'll notice that a lot of these were already factored, right? And we express them as, a product of linear factors, okay? In fact, you can always do that, especially over the complex numbers. But if you're restricting yourselves to the real numbers, you're going to get these things called irreducible quadratic factors. So let me go ahead and highlight this factor here, x squared plus 2, that sum of squares. This is an example of when we have an irreducible quadratic factor. Now, I won't get into the gory details here on what irreducible really means here, but it basically says you cannot factor this over the real numbers. So if you're trying to find the zeros of that thing there, so x squared plus 2 equals 0, well, if we think about it, right, we can subtract 2. And if I take square roots, well, the square root of a negative number isn't a real number. It's in fact a complex number. Okay, so the zeros that come out of this would be plus minus I times the square root of 2. Now, you can do partial fractions with complex numbers here, but we're going to go ahead and restrict ourselves to the real numbers here. If you feel so inclined, once you figure out how to do this real numbers, you can extend this to complex numbers, because then all you really have are just linear factors. But we're going to go ahead and restrict ourselves to just real numbers here. So how do we handle the irreducible quadratic? Well, first, okay, I know that I already have a linear factor here, just x here, because I have x minus 0 there. Okay, that guy there is just x minus 0. And now I'm going to handle the x squared plus 2. So I'm still going to put the x squared plus 2 in its own fraction, but what should go on the top? Well, in the worst case, okay, after I do my decomposition, the worst that this fraction could be and still be a proper fraction, so to say, is that this numerator can be bx plus c, some linear function. Okay, if I add the fractions, if I reverse the process again, get a common denominator and then add across the top, it should make sense that I should have something at worst linear. Okay, so that's how we handle the irreducible quadratic case there. And as you see here in part E, we also have irreducible quadratics. I have 2, and then I still have another copy here. Okay, both of these are irreducibles as well. Okay, the zeros of those things in pink are complex numbers, so they can't be factored over to reals. And we should also notice something here, something that I actually forgot to mention here. Partial fractions is useful when we have a rational function, so this kind of fraction, this ratio to polynomials, where the denominator has higher degree than that of the numerator. And I'm going to refer to that throughout the rest of the series as bottom heavy. So if we take a look here, okay, in A, we have a constant, which is degree 0. And on the bottom, if I multiply this out, this is a quadratic. So degree 2 beats degree 0. And this is bottom heavy, so I can do partial fractions here. Likewise, in B, this is a square on top, so that's degree 2. But on the bottom, I have degree 1 times the degree 2 thing. If I multiply that out, I get a square. So I'll have a degree 3 thing on the bottom. That's bottom heavy. Likewise here, this is bottom heavy because degree 4 beats degree 0. Degree 3 beats degree 2. And what about here? Well, on top, I have degree 4. On bottom, I have degree 2, and then I have a degree 2 squared, so that's a 4. 4 plus 2 is 6. If I multiply all this out, I get a degree 6, which beats a degree 4, so this is bottom heavy. And now, how do we set up the decomposition here? Well, we're going to go ahead and write, okay, for our first distinct irreducible, we have x squared plus 1, and at worst, that numerator is going to be linear, ax plus b. Now let's look at the next one. We have x squared plus 4. Okay, but we're going to have 2 copies of that. Okay, we're going to have 2 copies of x squared plus 4, but one gets a square. Okay, and of course, the numerators for these will, at worst, be linear. We have cx plus d in the second bit, and then ex plus f in the third. Okay, and so this is the recipe for partial fractions here. We want to break up these complicated fractions and write them as simpler looking fractions because in the end, I'm going to want to integrate them. And let's think about it, right? Okay, here in A, if I integrate this, well, I'll get some natural logs there. Okay, in B, I'll get a couple of natural logs here, and then this one in the middle, well, after a u substitution, that's a, another power rule, just some negative exponent stuff. Likewise here, we get some logs, and then negative exponents. We'll have a log here in D, and then if we do some work here, we might get a log in arctan, depending on what B and C are. And then similarly here for E. So, we showed the recipe, okay? We showed the recipe, and now I'm going to go ahead in the next part, demonstrate the method. Okay, we'll take the first 4 of those partial fraction decompositions that we just did, and we're going to go ahead and demonstrate the method of how we actually find those weights, A, B, C, and so on. And I'll see you in the next one.